Okay, lecture 4, domains, growth and decay, and logistic equation. And so we're going to talk about domains of solutions, which are a complicated problem, exponential growth and decay, and the logistic equation. So domains of solutions, what we've seen is that for autonomous differential equations, as long as your solution is trapped between two equilibria, the domain is all T. But if a solution can go to plus or minus infinity, then there's an issue with the domain. So dy dt equals y squared. This is a good example. So we'll sketch the phase line. Here's the phase line. This is y. The only equilibria is at y equals 0. And the derivative is always positive, right? Y prime is greater than 0 because when you square something, you get something positive. So there's our phase line. Sketch the solution curves for these initial conditions. What do they look like? Well, to draw the slope field, I'm not going to draw the whole slope field. There's t, there's y. We know y equals 0 is an equilibrium. And so our solution curves can't cross that. Y of 0 equals -1. That's down here, right? So we're starting at -1. And we know the derivative is always positive. So it's got to be always increasing, but it can't cross y equals 0. So it has to go up this way. And so it'll exist for all forward time because it's just going to get closer and closer to 0. But we don't know what happens in backwards time. Likewise, if we take y of 0 equals to 2, that's up here. So we're starting up here somewhere on the phase line. And we know in backwards time, it's coming from y equals 0. And in forward times, it goes forward, but we don't know what happens, right? Does it exist for all time as it goes up to infinity, or does it hit a vertical asymptote and suddenly shoot straight up? You can't tell from the differential equation, right? So you actually have to solve it. And this is one that we can solve. It's separable, and it's nicely separable. Dy dt equals y squared. So we separate the variables. We integrate both sides. -1/y equals t plus c. At this point, we know that y of 0 equals k, because that's our initial condition. So if we plug that in, we get k for y and 0 plus c. So -1/k equals c. So there's evaluating my initial condition, and that gives me -1/y equals t -1/k. And inverting it and multiplying through by -1 gives me that, where k is the initial condition. So there's our solution. So if we take y of 0 equals -1, that's this bottom curve. Then this becomes y equals 1 over -1 minus t, right? That's what we plug in for k. So at t equals -1, we have a vertical asymptote, right? Because if you plug in, -1. If you plug in -1, you'll get -1 minus -1, which is -1 plus 1, which is 0. So there's a vertical asymptote at t equals -1. And so what that's telling us here is that right here at -1, this curve has got a vertical asymptote. It's just going to go down to infinity. And so the domain of this solution is -1 to plus infinity. What about this curve? Y of 0 equals to 2. So if k equals 2, what do we get? We get y equals, now if we plug in 2 for k there, 1 over 1/2 minus t. T equals 1/2, you have a vertical asymptote, because at t equals 1/2, that's going to make this denominator equal to 0. So at 1/2, this one will have a vertical asymptote. And so the domain for this function is going to be -infinity up to 1/2. So these actually have vertical asymptotes. The domain is not defined for all t. You have to be able to solve the equation to figure out the exact domain. And in general, where the vertical asymptote is, depends on what your initial condition is, right? Every initial condition will give you a different vertical asymptote. So every solution has a different vertical asymptote that depends on its initial condition. And so you won't pick that up from either the slope field or the phase line or the differential equation unless you actually solve it. So a couple of examples. One is exponential growth decay equation, dy dt equals ky. Remember that a derivative is a rate of change. The rate of change of y is proportional to y. So whenever we have the rate of change of y is proportional to y, then we get our exponential growth and decay. And so this is a solution that's easy to solve. Dy dt equals ky. You separate the variables. Dy over y equals k dt. You integrate both sides, and then you get log of y equals kt plus some constant. So there's two cases here. If y is positive, that tells me that absolute value of y equals y. And so we have log of y equals kt plus c, or y equals e to the kt plus c, but we can do a little bit of simplifying there. Y equals e to the kt times e to the c, and I'll just call this constant a, so we get y equals a e to the kt. And note that the domain of this is all time. The second case is y is less than 0, and that tells me that the absolute value of y is actually equal to minus y. What's the absolute value of minus 10? It's minus 10 or plus 10. So then we get log of minus y equals kt plus c. We do the same steps. We get minus y equals a e to the kt, y equals minus a e to the kt. And since a is just some constant, we'll just rewrite this as y equals a e to the kt and just absorb the minus sign in the a. It's a little bit, I mean, we can do that because y is less than 0, and so the minus sign will be able to absorb into the a, but that gives us the same formula regardless of whether a is positive or negative. So that's nice. So what do the phase lines look like? Dy dt equals ky. There's two possibilities. One is k is greater than 0. So again, this is y. This is my phase line. Y equals 0 is the only equilibrium. If k is positive, then and y is positive, then this is going to be positive here. And if y is negative but k is positive, it'll be negative here. Y equals 0 here is a source. We call this exponential growth. K is less than 0. That switches all the signs. Y equals 0. Now we have decreasing and increasing, and this is a sink. Right? And sources are unstable. Stuff runs away from it. Sinks are stable. Stuff runs into it. So there's a solution for these sorts of things. So what kind of examples do we have? So depositing money into a bank account that offers 3% annual interest, compounded continuously. So if y equals the amount in, oops, I have space down here. Y equals amount in the account. right? And it's a function of t. Then the change of y over a particular time period is going to be 0.03 times y, right? How much interest do you get? You get 3% of what you have in the account. If you have $1 million, you get $30,000. If you have $1,000, you get $30, right? So it depends on how much you have in the account. And so your change is proportional to what we have. So this is a model for this. We think about delta y over delta t is going to be this. And then if we let delta t collapse down to 0, we get the differential equation dy dt equals 0.03y. And that's of the form that we just solved. K equals 0.3. This is supposed to be here. Here, k equals 0.03. So y equals some initial thing times 0.03 t. Great. So that's the question. What is A? We know the initial condition. Although it's buried in the word problem, y of 0 equals $1,000. So he deposits $1,000 into the bank account, right? So at time t equals 0. So that means that 1,000, that's my y, equals a e to the 0.03 times 0, because that's my t, so that equals a. So his bank account is 1,000 e to the 0.03 t. So after 3 years, how much does he have in the bank? Well, that's asking for t equal to 3. So y of 3 is 1,000 e to the 0.03 times 3. And you can grind that through a calculator and get 1094.17. Rounded off to the nearest cent. When will they have $7,500 in the bank account? Remember, $7,500 is the y, so that means I want to solve $7,500 equals 1,000 e to the 0.03 t. Solve that for t. How do you go about doing that? Divide both sides by 7.5. You get e to the 0.03 t. Take the natural logarithm of both sides. And remember that the natural logarithm of e raised to something is just whatever is in the exponent. Oops, got that backwards. T is log of 7.5 divided by 0.03, which is 67.16 years, because that's the units of time. So then you can figure out initial conditions. And so this is sort of a basic differential equation for bank accounts for calculating interest. Interest is a classic thing that increases by proportion to how much you already have. Exponential decay, a classic example of this is carbon-14. So exponential decay means that you lose a certain percentage of how much you have per year. And so your change in, that's a period, y equals amount of carbon-14. So the change in y over your time period is going to be some constant times y. Right? And so as we let dt go, delta t go to 0, we get dy dt equals ky. Rate of change of y with respect to t depends on your portion. So piece of wood has 34% of its original carbon-14. How old is the piece of wood? Well, we've got this, and we have this statement, and we have this statement, and we want to be able to answer this. So how can we do that? Well, half-life means that half of your initial amount has gone. So we know that the equation is y of t equals a e to the kt. And when t equals 0, we get y of 0 equals a. So the amount that we have is the initial amount times e to the kt. So half-life of 5730, that means when t equals 5730, y is 1/2 of what you started with. Right? That's what a half-life means. It takes 5730 for half of it to decay. So that allows us to evaluate what k is. So if we plug this in, we get 1/2 y0 equals y0 e to the 5730 t. Great. The y0s cancel out. We get 1/2 equals e to the 5730 t. Take log of both sides. And we can solve for t. And that's about notes here, 0.3 zeros and a 2 and a 1, 2. So that's fudge. We had put in t, so these should all be k's here. I apologize for that. K equals that. So that tells us that the amount that we have is the initial amount times e to the minus 0.00012 times t. Now, a piece of wood is found to have 34% of its original carbon-14. How old is the piece of wood? So 34% of its carbon-14. So that means that we've got 0.340 times y of 0. So the amount of carbon-14 I have is this much, and that should be equal to this equation. And we solve for t. And everything's done in percentages, right? So we can get rid of the y0s. We get log of 0.34 equals minus 0.00012 t, because when I take the log of this side, we just get the exponent there. And so t equals, if we solve that, 8918, about 1,000 years, 9,000 years. So how does carbon-14 dating work? Well, the idea is that the atmosphere is full of carbon. Some of it is carbon-14, which is radioactive and decays, and some of it is carbon-12, which is not radioactive and doesn't decay. So when you're alive, you're breathing in, breathing out, the proportion of carbon-14 in your body to carbon-12 is about the same as it is for the atmosphere. But when you die, you no longer bring in carbon-14, right? Your corpse isn't going to be bringing in any more carbon-14, and so that proportion of carbon-14 to carbon-12 is going to start decaying because the carbon-14 starts decaying. And so if we measure the relationship between, if you take a wood sample, it's got 34%, its proportion of carbon-14 to carbon-12 is 34% of what its original was. And so then we can figure out roughly what the dating, how old it is. There's a lot that goes into carbon-14 dating, and that's why when you get an answer like this, in real life, you'd say about 9,000 years. In math world, since we're doing everything precisely, we can say 89.13. Okay, so one thing to point out though is that the solutions to this, nope, we'll go all the way back up to here. The solutions, domains, it's just a nice exponential. Domain. Minus infinity to infinity, all t. No vertical asymptotes floating around. But we did notice for the y squared one that we did have vertical asymptotes floating around. So the logistic equation, and we'll talk more about this when we talk about bifurcations in a little bit. This model's growth that has a limit, dy dt equals ky times 1 minus y over n. So this is exponential growth, since we have k greater than 0. And this part is a cap on your growth. It's saying that when y equals n, you actually have an equilibrium. So the phase line for this, here's y, here's n, whatever n is, and here's 0. So my equilibrium are y equals 0, because that makes this 0, and y equals n, because that makes that 0. Those are equilibrium. If y is bigger than n, that means that this is positive and this is negative, because y over n will be negative. Y over n will be bigger than 1, and 1 minus it will be negative. So that's going down. If y is between 0 and n, this is positive and this is also positive, because this will be a fraction less than 1. So that's increasing. And if y is negative, then this thing inside the parentheses will be positive, because if y is negative, that makes this minus sign a plus. And if y is negative, this y is negative. So it'll be negative times a positive, and so that'll be decreasing like that. So there's the phase line. How do you go from phase line to solution curves? Well, we've got one solution curve. Y equals 0 is an equilibrium, and y equals 0 is a source. Everything's running away from it. Y equals n is the sink. And we have n as an equilibrium. And so what does solution curves look like? Well, if we're here, if we start negative, our solution curves should look like this. They're always decreasing because y prime is less than 0. If we're in between, we should be increasing. And if we're above here, we should be decreasing. So this kind of a model is, because y prime is negative up there. This kind of problem is used for a lot for animal growth, right? If you start with some few animals in a big space, right? They start, having babies, and then you have more and more animals. But there's a certain amount of animals that your ecosystem can contain, right? Just because of food and space regulations. And so there's some ideal population, which is n. And with this kind of model for population, your population always settles down to n, regardless of whether you start with too many or too few animals, you end up with n. Of course, this part down here, that's starting with negative animals, and you're not allowed to do that. So, logistic equation, there's our logistic equation. One thing to note is that the logistic equation is dy dt. God, my handwriting sucks. Ky minus ky squared over n. There's that y squared term. And so that's going to screw up some of our domains. So y equals t equals n is a stable equilibrium. All solutions with positive initial conditions will converge to that. K is called the growth rate, n is the carrying capacity. It's the number of creatures that your environment can support. More than n is too many, population decreases. Less than n is too few, population increases. So the logistic equation is separable. How do you solve it? And then we'll look at GeoGebra, because we don't want to solve it because it's pretty nasty, actually. Well, it's not nasty, but it's just a lot of work by hand, and we want to get to the differential equations aspects of this. So I'm going to simplify this a little bit by factoring out the n. that's in the parentheses, and that leaves me with n minus 1, n minus y, right? So if I multiply in this n in the denominator, I'll get n over n, that's my 1, minus y over n. So now this is nice and separable, and we get y over n minus y equals kn over dt. So we'll just separate the variables here, and we get this. And then integrate both sides. And that's everybody's favorite integration technique if you want to do this by hand. Partial fractions. So 1 over y and minus y turns out to be 1 over y minus 1 over y minus n. Oops, there's an n in front of both of these things. How do you deal with partial fractions? And this is sort of why I wanted to point this out. I go to Wolfram Alpha to do all my partial fraction decompositions. It's important to know that this is a partial fraction decomposition because it tells you what kind of terms to look for in the solution, right? Because if you're going to integrate this, you're going to end up integrating 1 over y minus 1 over y minus n dy, because that's your partial fraction decomposition, and that's going to give you logarithm terms. And then you have to wrestle with the logarithms and the signs to get everything to work out. But yeah, go to Wolfram Alpha to deal with partial fractions. And remember that partial fractions, when you're integrating partial fractions, you get logarithm terms. So we're going to actually go to GeoGebra to look at some solutions. If we look at our solutions here, and we think about the domains, solutions in here, domain should be all t. Domain here, we don't know, it should exist for time going forward. Domain here, we don't know, but it should exist for all time going backwards. So let's see what GeoGebra can tell us about this. So we'll go to different screen. There's GeoGebra, there it is. So first thing I'm going to do is type in the slope field. And I'm going to set k equal to 1 and y and n equal to 10. So there's our slope field. Excellent. And we have two equilibrium. We know one is at y equals 10, and we know that one is at y equals 0. Oh, equals 0. There we go. So there's our two equilibria, y equals 0, y equals 10. You can see everything above y equals 10 is going to come down. Everything between is going to rise up to y equals 10. Everything below goes down. So what does the solution curve that goes through the point 0, 12, what's the point, the solution curve that goes through there look like? Well, again, solve ODE by specifying a particular point. Our right side of equation is, I should pull this out a little bit so we can see it. Y times 1 minus y over 10. And then we want to start at the point 0, 12. And there's our solution. And it's kind of a weird solution. And I'm going to make it a different color. No, I think orange is okay. Because it gives us two branches, right? There's this part, which is the curve that goes through our initial condition, and there's actually this part. So we want to have exactly one solution for every initial value problem. And the problem is when you have a vertical asymptote, you have infinitely many solutions. As long as you keep the one that goes, the part of the graph that goes through the initial condition fixed, you could move this part up or down a little bit, actually in this case left or right a little bit, and you can get a another solution. So we don't want both parts of it. We only want the part of the graph that goes through here. And there's a vertical asymptote floating around, right? Where's the vertical asymptote? Here's the actual formula down here, minus 60 over e to the minus 6. So where's our vertical asymptote? We'll take the denominator and set it equal to 0. And this little equal sign means give me a number for that. So x equals minus 1.7918, more or less. So what have we got? We have way too many red lines. So I'm going to make this one a different color. Let's make it black. Well, maybe we'll make it dark blue instead. There we go. Okay, so what is this telling us? The solution that goes through our initial condition, which is this point A, has a domain that only goes back to minus 1.798. It's got a vertical asymptote there and it comes back down. And so when we go back and look at our solutions, we can say, well, if we start with too many, you actually have a vertical asymptote going to the left, but it exists all the way to the right. So suppose we change this though. Oops. Suppose we go to say 7. And we ask ourselves, if that's our initial condition, what is our solution going to be? So we'll get rid of these two things and we'll change our initial condition here to be 7. And so there's our solution in orange, and it goes up to 10 in forward time, goes back down to 0 in backwards time. If you look at the denominator for the equation, it's 3 e to the minus x plus 7. And we know that e to the minus x is always positive. So 3 times e to the minus x is always positive, which means 3 to the minus x plus 7 is always positive. There's no vertical asymptote here. This function is actually defined for all time. And so that works as we would hope it would for our solutions. So what we found then is here the domain is in fact all t, but here we actually have a vertical asymptote that cuts off our solution. And there's another vertical asymptote on the bottom. And so that is the logistic equation.